foundational guide for the atomic structure chapter, specifically tailored for the chemistry optional paper in the UPSC Civil Services (IAS) main examination. In the IAS main exam, this topic is part of Physical Chemistry, Paper I. Questions generally test your fundamental conceptual clarity, mathematical derivations, and the transition from classical to quantum mechanics. 1. Discovery of subatomic particles and Bohr's model. Before diving into quantum mechanics, it is essential to understand the limitations of classical models that necessitated a new approach. Bohr's model of the hydrogen atom, 1913, Bohr applied Max Planck's quantum theory to the Rutherford nuclear atom. Postulates. Electrons revolve around the nucleus only in certain selected circular paths called stationary orbits. While revolving in these orbits, electrons do not radiate energy. Only those orbits are allowed for which the angular momentum, L, of the electron is an integral multiple of frac h 2 pi. Where m equals mass of electron, v equals velocity, r equals radius of orbit, n equals principal quantum number, h equals Planck's constant, energy is emitted or absorbed only when an electron jumps from one orbit to another. Delta E equals E_2 E_1 equals h, nu. Key derivations, for hydrogen-like species with atomic number Z, radius, r_n, r_n equals, frac, n squared h squared, epsilon_0, pi mz e squared, approx 0.529, times, frac, n squared, z, text, r. Energy, E_n equals, frac, mz squared e caret 4, 8, epsilon_0 to the power of 2n squared h squared, approx minus 13.6, times, frac, z squared, n squared, text, ev, atom. Limitations of Bohr's model. It fails to explain the spectra of multi-electron atoms, only works for He, He+, Li, 2+, etc. It cannot explain the splitting of spectral lines in a magnetic field, Zeeman effect, or an electric field, Stark effect. It contradicts the wave-particle duality and Heisenberg's uncertainty principle by assuming precise paths for electrons. 2. Dual nature of matter and radiation. The failure of classical mechanics led to the birth of wave mechanics. De Broglie's principle, wave-particle duality. Louis de Broglie proposed that just as light exhibits both wave and particle properties, matter, like electrons, also exhibits a dual nature. Mathematical expression. Where lambda equals de Broglie wavelength, p equals momentum, derivation with kinetic energy, Ke, since Ke, E, equals, frac, 1, 2, mv squared, implies p equals, sqrt, 2 me. Heisenberg's uncertainty principle. It is physically impossible to measure simultaneously both the precise position and precise momentum of a microscopic particle like an electron. Mathematical expression. Where delta x equals uncertainty in position, delta p equals uncertainty in momentum. IAS main exam note. UPSC frequently asks conceptual or short numerical questions linking de Broglie's wavelength to the thermal energy of particles, or calculating uncertainty. 3. Quantum mechanical approach to atomic structure. This forms the core of the Advanced Atomic Structure syllabus in Paper I. The Schrödinger wave equation. Schrödinger incorporated wave-particle duality into a wave equation to describe the behavior of an electron in an atom. The time-independent Schrödinger equation is written as, or in operator form using the Hamiltonian operator, hat, h. Where psi equals wave function, E equals total energy, V equals potential energy, significance of psi and psi squared, psi, wave function. It is an amplitude function. It has no direct physical significance on its own. It can have both positive and negative mathematical signs. Psi squared, probability density, according to Max Born, psi squared at any point represents the probability density of finding the electron at that specific point in space. 4. Quantum numbers and orbitals. Solving the Schrödinger equation for the hydrogen atom yields 3 quantum numbers, while the fourth arises from the relativistic properties of electron spin. Quantum number. Symbol. Allowed values. Physical significance. Principal n. 1, 2, 3, dots. Determines the main energy level, shell, and size of the orbital. Azimuthal, orbital angular L. O, text to, n1, determines the subshell shape, L equals 0, right arrow S, L equals 1, right arrow P, L equals 2, right arrow D, L equals 3, right arrow F. Magnetic m_LL, text to, plus L. Determines the spatial orientation of the orbital in a magnetic field. Spin m_s plus, frac, 1, 2, frac, 1, 2. Indicates the orientation of the spin axis of the electron. 5. Radial and angular wave functions. For a hydrogen-like atom, because of spherical symmetry, the wave function psi, x, y, z is converted into spherical polar coordinates psi, r, theta, phi, and split into two independent parts. Radial wave function r, depends only on the distance r from the nucleus. It determines the size and radial nodes of the orbital. Angular wave function y, theta, phi, depends on the angles theta and phi. It determines the shape and directional orientation of the orbital. Concept of nodes. Nodes are regions in space where the probability density of finding an electron is 0, psi squared equals 0. Radial nodes, spherical nodes, n, L1. Angular nodes, nodal planes, L. Total nodes, n, L1, plus L equals N1. 6. Rules for electronic configuration. To fill electrons in multi-electron atoms, three fundamental principles must be strictly followed. Aufbau principle. Electrons are filled in orbitals in the order of increasing energy levels. The energy of an orbital is determined by the n plus L rule. If two orbitals have the same n plus L value, the one with the lower n value is filled first. Pauli's exclusion principle. No two electrons in an atom can have the same set of all four quantum numbers. Consequently, an orbital can accommodate a maximum of two electrons, and they must have opposite spins. Hund's rule of maximum multiplicity. Pairing of electrons in degenerate orbitals, orbitals belonging to the same subshell with equal energy, like p_x, p_y, p_z, does not take place until each orbital is singly occupied with parallel spins. This minimizes interelectronic repulsion. High-yield topics for IAS mains, trend analysis. When preparing notes for revision, ensure you can comfortably write 10 to 15 mark answers on these recurring themes. Derivation of the Schrödinger equation for a particle in a 1D box and its application. Plotting radial probability distribution curves, 4 pi r squared VSR, for 1s, 2s, 2p, 3s, 3p, and 3d orbitals. Explaining the physical difference between an orbit, classical, and an orbital, quantum. Exceptional electronic configurations, e.g., crossing, Cu, GD, and the stability of half-filled and fully filled subshells due to exchange energy and symmetry.